All right, so we've done some work here and we've figured out the current phasor for this circuit. We know the RMS voltage and the RMS current at the source. So let's go ahead and just grab what we've already determined and just bring it over to the next slide with us. I think it would probably be helpful to have the circuit itself too. So let's just grab that. Put that there. And then we can grab our things that we've boxed. Also, we'll just grab the time domain stuff too. How about that? Just get all this stuff. Bring it on over with us. All right. Let's rearrange some stuff. Let's grab this and put it here. I'll grab this, put it here, and this, and put it here. So we got our voltage stuff, our current stuff, and what we wanted to do was we wanted to find the average power and the apparent power. The apparent power is super easy to calculate, right? It's just IRMS times VRMS, and we have both of those quantities. So let's go ahead and say that the apparent power is going to be 120 volts RMS multiplied by 11.24 amps RMS. Looks like it says arms, but it is amps RMS. And we know that the units for apparent power are in volt amperes. So do not write this in watts. It's not watts RMS. It is a volt amperes. So we're going to write VA when we make this computation. 120 times 11.24. And I get 1348.8 volt amperes for my apparent power, okay? So that is my apparent power. S is equal to 1348.8 volt amperes, okay? All right, so that's my apparent power. Now I need to calculate my average power, or my real power, P, which is basically my apparent power multiplied by the cosine of my phase, which is the phase of the voltage minus the phase of the current. In this case, it is the cosine of 0, because there's no phase shift on my voltage waveform, right? 0, minus negative 20.65. All right, which results in S times the cosine of 20.65 being my real power. Okay, so then we can say that my real power is equal to 1348.8 volt amps. And that's going to be multiplied by the cosine of 20.65. And I will throw that in my calculator. And again, average power is measured in watts. So I know this gets a little bit confusing and you're probably wondering why, but it's all just to distinguish one quantity from the other. I calculate 1,262.1 watts, or 1.262 kilowatts for my average power. And so you can see that my average power is slightly less than my apparent power, right? I have 1348.8 volt amperes for my apparent power, and I have 1,262 watts, or 1.262 kilowatts for my average power. There is some discrepancy here. There's about 100 watts or 100 volt amps missing. Well, I guess it's closer to 90 something or 80 something. But nonetheless, where does that power go? Well, that is what's called reactive power. And that power is basically oscillating back and forth between the inductor, which can store energy, and the source, and it doesn't get delivered to the load. That is my reactive power. And that's what we're going to talk about in the next video, is reactive power and how to calculate it. And then we're going to take a look at the power triangle, because we've now basically, once we cover reactive power, we've covered all the important aspects of AC power, which are apparent power, real power. Again, this is just the same thing as the average power that we calculated at the beginning. Sometimes it's even called true power. There's all these different names for all this stuff. And so we're going to take a look at reactive power in the next video, which is basically how much power is oscillating back and forth between the inductor and the source and not getting to the load. And then we'll take a look at the power triangle, and we'll do some more example problems. All right, so I'm going to go ahead and end this video right here, and we'll talk about reactive power next.